The following review slides are based on the energy objectives, so on the back of the land and water objectives. And these will be due in class on Tuesday, and your quiz will be on both land, water, and energy. Objective number 1 says to know the source of energy on Earth and the process that transforms the energy into that energy into chemical energy. And just to go through the PowerPoint slides, I think that there are a few extra slides in the beginning that I'll go over before I answer that. Laws of thermodynamics, really important that you have an idea of the laws of thermodynamics. We talked about this in the first quarter, but remember that we have an open and closed system, and we talked about an open system is any system where energy can be transferred in or out of that system. In a closed system, there's no energy transfer. Your first law of thermodynamics states energy cannot be created or destroyed. So the same amount of energy is present, it's just in different forms. And your second law of thermodynamics, when energy is converted from one form to another, a less useful form results. So we're really talking about the energy quality. So you can see our food chain here and our trophic levels. And that is energy is passed from one trophic level to another. Energy is lost as heat for this specific. 90% is lost as heat. And this means that entropy is going to increase. So entropy is a randomness or disorder in a system. And so the entropy increases. Don't forget your potential versus kinetic energy. Potential energy is energy that is stored. Our kinetic energy is energy of motion. So you can see here with his bow and arrow, the energy is stored, and as soon as he lets go of the arrow, then it's transformed into kinetic energy. I believe we looked at this roller coaster, and you can see that we have our kinetic and potential energy and time. And you're going to have greater potential energy at the top of the roller coaster as well as at each loop, at the top of each loop. We have a mouse trap, which is an example of potential and kinetic energy. And you throw a ball in the air. It's going to have more potential energy right at that split second where it's not rising anymore or falling. Roller coaster. Gasoline has potential energy that is converted into kinetic energy by the engine. And then when potential energy is used up, you're out of gasoline. So only 20% of the energy in gasoline is actually converted to mechanical energy. The rest is lost as heat. So again, for number 1, it says know the source of the energy on Earth. You need to know that the sun is the main source of energy on Earth. So our sun is going to give us radiant energy. In the process of photosynthesis, which you know by green plants and algae, is a process where that radiant energy is converted into chemical energy. So we have our leaves here, which contain our chlorophyll, that green pigment, and our chloroplasts. And you probably remember the intricacies of photosynthesis from biology. Good equation to know for photosynthesis. So again, this energy is originating from the sun. Photosynthesis, we have 6 molecules of carbon dioxide. We have 12 molecules of water. We have light. And then we have this C6H12O6, our glucose molecule. This is our chemical energy. Our 6 molecules of oxygen and our 6 molecules of water. By looking at this equation, you could tell me that trees and plants are carbon sinks. You see that the carbon dioxide is a reactant here. And they're important because they provide us with oxygen, which is needed in cell respiration. Another good equation would be our cell respiration. Here we have that glucose molecule, our C6H12O6, oxygen and water, goes through cell respiration, and then we have our carbon dioxide, we breathe out, water, and then our chemical energy into ATP, adenosine triphosphate. And eventually this becomes mechanical energy. So we're going to use this for movement. Number 2, it says compare renewable and non-renewable resources. So just to compare them for you, renewable, any natural resource that once consumed cannot be replaced. Renewable, natural resource that can be replaced. Some examples of non-renewable resources: oil, which makes gasoline. Minerals are an example of a non-renewable resource. So it's supposed to be a diamond. Coal. Natural gas is non-renewable. Uranium, which is a mineral, that's non-renewable and used as a fuel. Your renewable resources, some examples here, we have trees, which is biomass. Solar, wind, these are all renewable resources that are driven directly or indirectly by the sun. If I had to name one that is not directly driven by the sun, unrelated to the sun, a renewable resource, that would be geothermal. And we'll look at geothermal in a second. Non-renewable. So let's look at coal. If you are looking in your Barron's book, the one that I gave you, it's old, has wrong information for your reserves of coal. Remember, reserves are identified and extractable today. A resource means we've identified it, but we may not have access to it yet for whatever reason. So reserves are what we're able to extract today. So we have coal. Our major countries that have coal reserves: United States #1, Russia, and then China. So your top 3. You should know that we have approximately 200 years of coal reserves. You should know that we have different grades of coal. So our lowest grade would be lignite. Then a middle grade, in our textbook we looked at subbituminous, then bituminous. I believe in some of the review books you only see bituminous, they don't even include subbituminous. So it goes lignite, subbituminous, bituminous, and then the highest grade of coal is anthracite. The most used would be bituminous. We've largely exhausted the anthracite. Sometimes you'll see peat added in for the grades of coal. Peat is like a precursor to coal. It's really just plant matter, and that would go before lignite. How is coal formed? Remember, 300 million years ago, We had swamps and marshes filled with plant matter. That plant and debris was covered by soil. Heat and pressure from within that in the earth converted that plant material into our coal. Coal is the dirtiest of the three fossil fuels. Coal produces high amounts of sulfur dioxide, as well as mercury. So the combustion of coal, sulfur dioxide, mercury, along with carbon dioxide, carbon monoxide, and the other emissions that we talked about with air pollutants. Coal is used to produce electricity. And some air pollution control devices we're going to talk about in a second. You know that a wet scrubber is used to reduce sulfur oxides, and an electrostatic precipitator can also reduce particulate matter. Oil. About 65% of all of our reserves, you can see, are found in the Middle East. You should think we have oil in Saudi Arabia, Iraq, Iran, Kuwait, those Middle Eastern countries, as well as Venezuela, Ecuador. We estimate our reserves at about 50 years. And oil was formed a little different than coal. Instead of our plant material, we have microorganisms that were broken down with the heat and pressure from within the earth. You should know that oil is the #1 energy for commercial energy use today. So for commercial. And for developing countries, remember biomass, the main energy source. Natural gas, the third fossil fuel. You can see Russia and Kazakhstan, which is missing an H. About 40% of natural gas reserves. Our estimates vary for the amount of natural gas we have left over as far as a number of years. Some estimates are as low as 58 years and some as high as 98 years. Again, with the reserves of all of these, as we get better technology, we'll be able to make some of those resources, those identified deposits, reserves, and we'll be able to access them. The big thing about natural gas is it is the cleanest burning of the three. Natural gas could replace coal in order to produce electricity. Nuclear is also non-renewable. Nuclear, we're really talking about uranium. So uranium is the mineral, which is the fuel for nuclear energy. Australia and Kazakhstan for our reserves of uranium. Remember our isotopes of uranium. Our uranium-235 is used in conventional nuclear fission. So we're talking about nuclear fission here, not nuclear fusion, nuclear fission. U-238 is the most common isotope of uranium. But U-238 decays into plutonium-239, which could be used in breeder nuclear fission. We don't use breeder nuclear fission in the United States. We use conventional. Conventional nuclear fission, we have our uranium-235 atom here. A neutron is going to hit our U-235 atom, and we're going to see some free neutrons that are going to be released from the atom. This is going to start a chain reaction. So once these are released, it's going to hit another uranium-235 atom, and when this happens, these atoms split, we have high amounts of heat energy. So this energy here is in the form of heat. It's a chain reaction, but it's a controlled chain reaction. We look at our nuclear power plant. Don't forget the different parts of a nuclear power plant. Something that we have now that we did not used to have is a containment building. So this containment building is a 3 to 5 foot wide concrete building which protects our reactor core where the nuclear fission reaction is taking place. If you remember Chernobyl, the accident in Chernobyl, there was no containment building. So this is a safety measure. Inside of our containment building, we have our reactor vessel and our reactor core. This is where the fission reaction is taking place. We have control rods. You can see them right here. The control rods are made of metals such as boron, which will absorb neutrons, so they will stop the reaction. So if we want to turn off the reaction, we want to stop producing electricity, maybe for maintenance, we lower the control rod into the reactor core. The control rods will absorb the neutrons, stopping the reaction. So this is something that needs to take place over a period of hours. Inside our reactor core, we have liquid water, which is under very high pressure. So that water is going to stay in a liquid state. It's not going to evaporate into steam. And you can see that it's going to move throughout the primary circuit. It's going to move in this direction over and over and over again. It's highly radioactive because it's coming into contact with the reaction itself. The secondary loop, here we have our secondary loop. We have this water that is coming into a heat exchanger or a steam generator. And now we have the heat from the primary circuit transferring into the steam generator. The water here changes into steam. That steam goes into a turbine, spins the turbine, which is connected to a generator and produces electricity. So nuclear power for producing electricity could be replacing coal, the burning of coal. After that steam is done turning the turbine, it would move down here to a condenser where colder water from the tertiary circuit is going to condense that steam into a liquid, and then this water is going to go throughout the secondary circuit again. We have the water coming in from a cooling tower or a lake. This water is used to cool down the inside of the nuclear power plant. So the water is coming in. That heat from the secondary loop is going to transfer into the condenser, and then the heat will leave the nuclear power plant by the tertiary circuit. The tertiary circuit does not contain radioactive water. Two major problems with nuclear power, with the production of electricity using nuclear. The biggest issue is radioactive waste, so disposing of radioactive waste. The next issue, if we wanted to talk about pollution, there's no real pollution coming from this cooling tower. We don't have carbon dioxide and sulfur coming from this cooling tower. No ash. But instead, many times nuclear power plants are built along coastlines so that this heated water is going to go out to an estuary, and it's called thermal pollution. So this water is going to be heated. It's going to heat up the surrounding water. I think I told you that manatees, they are attracted to nuclear power plants because of the warm water during the wintertime. And the problem with the warm water is that it lowers the dissolved oxygen in the water. So that can negatively affect fish and aquatic organisms. Okay, so breeder nuclear fission. So note that breeder nuclear fission is different from our conventional nuclear fission. Breeder nuclear fission is going to use a different fuel. In conventional, like we said, we use uranium, specifically isotope U-235. In breeder nuclear fission, they are able to use uranium-238, which can be made into plutonium-239. Plutonium is used in our breeder nuclear reactors. You can see here it says generates more electricity than conventional nuclear fission. And it uses a liquid sodium as the liquid in the primary circuit, and it's very reactive. If liquid sodium comes into contact with oxygen, then it can be explosive. But breeder nuclear fission, other countries continue to use this. It actually generates more fuel than you start with. So this is helpful because you can reuse and recycle some of this fuel versus having to end up with waste in which we don't know how to dispose of the waste or have a good place to put the waste. So radioactive waste, like I said, this is one of the major problems associated with producing electricity using nuclear fission. So a lot of students at first, you think, oh my goodness, it must be dangerous because of the risk of accidents or because of accidents that you've heard in the past. Radioactive waste, what's left over is really the main problem that we deal with when it comes to using nuclear fission to produce electricity. So the problems here, nuclear waste, it's going to take millions of years to degrade. We don't know where to put them. Currently, nuclear power plants can be used for up to 40 years. After that, they can be renewed. So their license can be renewed. And if it is to be closed down, then decommissioning has to take place. So basically, to disassemble the parts of the nuclear reactor and then place this waste or these highly radioactive substances on site for right now. So we have low-level radioactive waste and also high-level radioactive waste. Low-level radioactive waste is going to include anything that gives off small amounts of radiation. So paper, clothing. Many times we can just wait for this waste to become less radioactive and dispose of it in a regular landfill. High-level radioactive waste gives off high amounts of ionizing radiation. And you can see here some examples would be the fuel rods, the coolant fluid, so that water under high pressure in the primary circuit, that would be an example of high-level radioactive waste. Currently, we don't have a permanent storage site for our radioactive waste, our high-level radioactive waste. So most of our high-level radioactive waste is kept on site. You can see in pools many times, so it's put into barrels and kept in pools, or even above ground casks. So you can see right here, these are large steel casks that are guarded that contain high level radioactive waste. So we use nuclear fission. Nuclear fusion is the process of taking deuterium and tritium. These are both isotopes of hydrogen, heating up temperatures extremely hot to force the nuclei to fuse together. And that's showing you here deuterium, tritium. Large amounts of energy are produced. The positives of fusion, these isotopes right here of hydrogen are abundant. So we can extract them from seawater. They're found in nature. And it produces a lot of energy with minimal nuclear waste. And that's nuclear fusion. We talked about the tokamak and possibility of one day of fusion. If you look at the Barron's book, gives you some positives and negatives of your fossil fuels for the older book on page 235. Definitely a good thing to kind of look through. Okay, cogeneration. Number 3. Cogeneration is using one fuel source for multiple uses. So for example, if my fuel input here is coal, I'm going to burn coal. It's going to produce electricity, but the waste heat will be used for either industrial processes, to heat buildings, additional electricity, or hot water heating. So cogeneration is using one fuel for multiple uses. The waste heat is recovered and used. And it makes sense. Why would we not do that? Okay. Here we have our passive and active solar heating. We're kind of jumping around here. So if you move down to number 8, it says to compare and contrast passive and active solar heating. What you need to know by looking at this picture, this is showing you passive solar heating, is that passive solar heating is a way to heat a home by utilizing the greenhouse effect. So if you remember looking at this picture here, this would be a house in the northern hemisphere. And we said that the summer sun, we'd want a longer overhang here. And even though it's called passive solar heating, it's to heat up inside of a house without using pumps or a series of devices. It's also going to help keep it cool in the summertime. So here we have our summer sun that's very high in the sky. The solar radiation is being blocked out by this extra long overhang. But in the wintertime, when the Earth is facing away from the sun, the winter sun is going to make its way into the home. And you can see that we have south-facing double-paned glass here to allow that light to enter. And the greenhouse effect, we have that radiant energy that enters, but that infrared heat that gets trapped inside. So it's going to heat up this home without having to use any pumps or devices. And this is showing you passive solar heating. You look at this picture over here, another example of passive solar heating. Again, we're using the greenhouse effect here. You have an extension on your house. These dark colored barrels or drums can be filled with water. The solar radiation is going to penetrate through the glass. It's going to be absorbed, that radiation, by these drums, and then the heat is going to radiate off, entering the home and warming the home. So again, these are both examples of passive solar heating. Active solar heating, you can see, looks different. This is using a series of devices in order to heat up water. And so many times we have some type of solar collector. So this can be on a roof of a home. There could be a heated liquid like oil that's going to run throughout these tubes. That oil will go to a heat exchanger where that heat will be transferred into our water. So here's our storage tank filled with water. That water will get heated, and then you will have hot water that will come out of your sinks or to your pool. So active solar collectors that use the sun's energy to heat water for inside a home or business. Now this could be very inefficient. So a con for this would be very inefficient. Also depends on the season. This is showing you a solar cell, and I have a big arrow. This has nothing to do with active and passive solar heating. So active and passive solar heating, this is to heat up homes or water. The reason why this does not count here, this solar cell, is because it produces electricity. Now moving on to number 4, which I don't think that we answered. Electrostatic precipitators and scrubbers. So remember scrubbers, also known as a desulfurization system. The reason why we'd want to use a scrubber, also known as a wet scrubber, and you can see a picture here, is that it causes sulfur oxides like sulfur dioxide and particulate matter to precipitate out of the flue gas. So we're able to collect this in a solid form, and then we have to dispose of this solid material. Water with chemicals, we're really talking about limestone here, where calcium carbonate is mixed with water, sprayed down, you can see, through a smokestack, and it helps remove that sulfur. Something else that's not listed here, but just to remind you, we could use fluidized bed combustion. Same idea. This is the picture down here with the limestone and the coal. And it burns at a lower temperature, so it's going to reduce the amount of nitrogen oxides and sulfur oxides. And so we're able to collect a lot of that sulfur, and it's going to reduce acid rain. And then your electrostatic precipitator. If you remember, this also can go into a smokestack, but basically we have particles here. It removes particulate matter, so waste gases containing smoke particles. There's a little grid here, going to give these particles a negative charge. Those particles are going to move upward. They're going to adhere or stick to positively charged collecting plates. And then we have a little collecting area right here where we can capture those particulate matter particles and then dispose of them. Depending on what's in them, they may go to a hazardous landfill. And for your energy, I believe that is it. So hopefully this was helpful. And don't forget to turn in your energy and land and water objectives in the beginning of class tomorrow. And you will have a quiz on this information.